Okay, everyone. Now we're going to start the chapter 6. So actually, chapter 6 is another very important chapter. It mainly describes circular motion, orbits, and at the end, we're going to talk about gravity. Okay, let's start this chapter. So you will have some questions before the chapter, which is the reading questions. Um, so I suggest you to go through the questions and see if you understand all the questions and answers after this chapter. Okay, so first of all, um, circular motion. So we have mentioned the circular motion a little bit before, and here we want to discuss the simplest circular motion, which is uniform circular motion. Okay, so for uniform circular motion, it's a specific circular motion that in this motion, the speed of your object is a constant. So that's why it's called uniform circular motion because the speed is uniform. So its velocity is not constant. Okay, so let me change the cursor into pen. So its velocity is not a constant. Why? Do you remember the difference between speed and and velocity? So the difference is direction. Because even though the speed in the circular motion could be a constant, however, the velocity cannot because the velocity includes a direction. So for example, in the circular motion, the direction of the motion is always changing. So the velocity is not a constant. It's changing all the time. And we have learned the way to calculate centripetal acceleration in the previous chapters. The acceleration is calculated in this equation, A equals to v squared over r. If you forget how to derive this equation and how to use this equation, please go back to your previous chapters and see the details of this equation. This is centripetal acceleration equation. Using this equation, when you have the speed and the radius of the circular motion, you can calculate the acceleration, which is the centripetal acceleration. And also, the direction of the centripetal acceleration is always pointing to the center of your circular motion. Okay, now let's ask a quick question. A ball at the end of string is being swung in a horizontal circle. The ball is accelerating because of what? So I will please pause your slides, your video actually, and um, and restart the video when you finished your choice. Okay, so the answer is the direction is changing. So this is the thing we discussed here. So even though the speed is constant, but the velocity is always changing. So there need a acceleration to change the velocity. And the velocity is changing simply because the direction is changing. Okay, now a car is turning at a tight corner at a constant speed. A top view of the motion is shown in this figure. The velocity vector for the car points to the east at the instant shown here. What's the direction of the acceleration? Okay, now the car is making a circular motion like that. So if the motion is circular motion, then the direction of the acceleration is always pointing to the center of the circular motion. So that's the direction of acceleration. Okay. The time interval it takes an object to go around a circle once is called the period of the motion. So that's the concept of period of the circular motion. That's pretty straightforward. We don't want to explain it more. And from the period of the motion, you can calculate the frequency. We can specify circular motion by its frequency. The number of revolutions per second is the frequency. Usually we use F, stand for the frequency. F equals to 1 over t. T is a period. And the SI unit of frequency is inverse seconds or per second. And the speed can be calculated by the length of the circle over the period, which is 2 pi r over t, because the length of the circle is 2 pi r, so 2 pi r over t, that's the speed. And remember that t equals to 1 over f, because f equals to 1 over t. That's the equation we learned here. F equals to 1 over t. So 2 pi r over t also can be written in this format. V equals to 2 pi r times f, or V equals to 2 pi r over t. They're the same. And we can combine this with expression of the centripetal acceleration. We have learned this centripetal acceleration in this way, a equals to v squared over r, and v could be written in 2 pi f, which is here, 2 pi f r squared, and over r you will get 2 pi r squared times r, or written in another way, which is 2 pi over t times r squared. This is from this equation here. Okay, so here are several different ways of calculating the acceleration, the centripetal acceleration. You don't have to remember all of the equations, you just need to remember one of them. Most probably, let's remember this one, because once you know this one, then v equals to 2 pi r over t. That's pretty straightforward. You can get this one. Or 2 pi r times f equals to v, then you can get this one. So just remember one equation, you should be able to solve similar questions. Now let's see one question here. An audio CD has a diameter of 120 millimeter and spins at up to 540 revolutions per minute, RPM. When a CD is spinning at its maximum rate, how much time is required for one revolution? If the speck of dust rides on the outside edge of the disk, how fast is it moving? And what's the acceleration? Okay, so totally there are 3 questions. Number 1 question, how much time is required for one revolution? So what's that? This is t. Period. Period is the time required for one revolution. If a speck of dust rides on the outside at the edge of the disk, how fast it's moving? That's v, speed. What's the acceleration? That's a. Okay, so first let's calculate t. We know it spins 540 RPM, so 540 revolutions per minute. Then that means in 1 minute there's 540 circles, and we want to calculate t. So how much time is required for one revolution? We know for 540 revolutions it needs 1 minute or 60 seconds. Then what we can do is t equals to, let's say, totally we have 60 seconds for 540 revolutions. Then you use 60 over 540, then you have the time. So using this equation, you can calculate t. So t equals to 0.11 second. So the period is 0.11 seconds. And here, in textbook, it gives you another way to calculate it. It first calculate frequency, and then from frequency you calculate period. Yeah, you can use this way, but so here I think this way, calculating the period directly is more straightforward because you have the total time 60 seconds, you have total revolutions 540. You just use time over revolutions, you get the time needed for one revolution. That's more straightforward. So the answer is the same, 0.11. Okay, now if a speck is on the edge, okay, so the speck will have a circular motion. Let's say the speck is here, so it's moving in a circular motion. And the R, the radius, is 120 millimeters or 0.12 meters. That's the radius. So you have the radius, you have the time or period. Can you calculate V? Yes, V equals to 2 pi r over t. You know r, you know t, so you can calculate the velocity. So V equals to 2 pi r over t. Okay, 2 pi r over t, or 2 pi r times f, because 1 over t is f. So finally you will get the answer, 3.4 meters per second. And then finally, what's the acceleration? A equals to v squared over r. Then you use a equals to v squared over r. So you know r, and you know v is calculated here, so you can calculate the a, or acceleration. And in the textbook, it uses another equation, 2 pi f squared times r, as I said. So there are several ways to calculate acceleration. So either way is good. So I prefer to use this equation, v squared over r. So if you use v squared over r, you will have the same answer. Okay, so that's the question of circular motion on the disk. Okay, next section, the dynamics of uniform circular motion. Riders traveling around a circular carnival ride are accelerating. As we have seen, the F net or net force equals to ma is the acceleration, m is the mass, or mv squared over r. This is Newton's second law, and a, due to the equation we learned before, here a equals to v squared over r, plus the Newton's second law. Finally, you know ma equals to mv squared over r, and the direction of the net force or acceleration is towards the center of circle. Okay, so here is the dynamics of uniform circular motion. A particle of mass m moving at constant speed v around a circle of radius r must always have a net force of magnitude of mv squared over r pointing towards the center of the circle. Okay, so this is talking about the force in a circular motion. In a uniform circular motion, there's always acceleration which is pointing to the center. It's called centripetal acceleration. Because there's acceleration and you have a particle which has mass which is m, then you should always have a net force which is pointing to the center. This is called centripetal force. This force provides you a centripetal acceleration. And due to the Newton's second law, we know F net equals to ma. So this is a connection between centripetal acceleration and centripetal force. And this force is not a new kind of force. The net force is due to one or more of our familiar forces such as tension, friction, or normal force. Okay, now let's see some examples. A ball at the end of string is being swung in a horizontal circle. So what force is producing the centripetal acceleration of the ball? Please make your choice. Please pause the video until you find your answer. Okay, now I suppose you have made your choice. The answer is the tension of the string. So when you're swinging the ball with a string, actually it's the tension providing the centripetal acceleration. Now, another example, a ball at the end of the string is being swung in a horizontal circle. What's the direction of the net force on the ball? This is a pretty simple and straightforward question. We have been talking about this many times. First of all, what's the direction of the acceleration on the ball? It's to the center. And what's the direction of the net force on the ball? It's to the center. That's called centripetal acceleration or centripetal force. So here, an ice hockey puck is tied by a string to a stake in the ice. Okay, so here's a figure. The puck is then swung in a circle. What force is producing the centripetal acceleration of a puck? So which force do you think is providing the acceleration? So first it mentions it's ice. Let's ignore the friction. So if there's no friction, what is providing the acceleration? And of course, the acceleration is always pointing to the center of the circular motion. And then it's not difficult to think that the string will provide the tension or the centripetal force. Because if you cut the string, you can imagine it won't have this circular motion. The part will just go away straightly if there's no tension force. Now, let's see another example. A coin is rotating on a turntable. It moves without sliding. At the instant shown in the figure, which arrow gives the direction of the coin's velocity? Okay, so that's a table. Here is a coin. This is a top view of the coin on the table. When it's in the rotation, so what's the instantaneous velocity at this moment? So the answer is A, the tangent direction. Now, the same coin on the same table. The question is changed. Which arrow gives the direction of the frictional force on the coin? That's a little bit tricky question. So what's the direction of friction? Since the coin is rotating in a circular motion in this way. So what do you think is the direction of the friction? The answer is D. Is that surprising? Actually, no, because you can imagine, first of all, if there's no friction, the corn will not go into a circular motion. And in a circular motion, there must be a centripetal acceleration and centripetal force, which provide the centripetal acceleration. And the centripetal force has to point towards the center. This force has to be the friction. If there's no friction, there's no uniform circular motion at all. So the net force has to be pointing to the center, which is um, the friction, because friction is the only force which can provide uh, the net force pointing to the center. Now, the same coin on the table, and it's rotating. It moves without sliding. At the instant shown here, suppose the friction force disappeared. In what direction should the coin move? That's a little bit tricky. Now, let's say when it's moving in a circular motion, there has to be um, friction. If suddenly the friction disappeared, in what direction should the coin fly to? So the answer is A, because at this moment, the velocity of the coin goes up in direction A. So if there's no friction at all or no net force, it will keep going in the direction of A. This is due to the Newton's first law. If there's no net force, the object will keep going in the direction, and it will be undergoing uniform motion. Okay, so let's see some applications of circular motion of the centripetal acceleration and centripetal force. So engineers design curves on road to be segments of circles, for example, which is shown here. They also design dips and peaks in roads to be segments of circles with a radius that depends on expecting speed and other factors. When a car is moving at a constant speed and goes into a dip shown here, at the very bottom of the dip is the normal force of the road on the car greater or less or equal to the car's weight? Let's think about it. If you drive car into a dip, then at the dip, first of all, do you feel heavier or lighter? If you feel heavier, that means the normal force is greater than your weight, because the normal force is the weight you can feel, which is called the apparent weight. Do you remember that? So intuitively, do you think you will be feeling heavier or lighter at this position? It will be heavier. That means the normal force is greater than the weight, as the free body diagram shows here. Normal force greater than weight. Why? Because only in this situation, your net force is going up. And in this case, your net force has to be going up, because the acceleration is pointing to the center of the motion. So the acceleration is going up, so the net force has to be going up, then the car can move in this kind of circular motion. Another question. A car is turning in a corner shown here at a constant speed following a segment of circle. What force provides the necessary centripetal acceleration? So this is a very common question in your daily life. When you make a turn by your car, you know it's making a turn in this way, so it has to be a centripetal acceleration in this direction. And then there has to be a net force which provide um, the centripetal acceleration. So what force is providing this centripetal net force? The answer is friction, as shown here. The friction of your tire is providing the centripetal acceleration. Imagine if there's no friction at all. Let's say if you're driving on ice, then do you think you can make a sharp turn? It's very difficult. And if your tire is not made by some materials which has a high coefficient of the friction, let's say if your tire is made of ice and you're driving on the ice, so ice to ice, that's almost frictionless. Do you think you can make a turn in this situation? No, because in this case, you don't have enough friction which can provide the centripetal acceleration, so it's difficult to make a turn. So actually in daily life, your tire is very important, not only for acceleration, but also for making a turn. Because when you're making a turn, it needs your tire to provide centripetal accelerations from the friction. Okay, so the tire is very important. So when you drive a car, make sure you check the tire frequently. If the tire is too old, you just remember to change the tire. Okay, now let's see another example. A hollow tube lies flat on a table. So here's a top view of the table. There's a tube. You put a ball with the initial velocity. Then the ball will run in the tube, and the ball is shot through the tube. As the ball emerges from the other end, which path does it follow? A, B, or C? Okay, let's see. When the ball is in the tube, the wall of the tube will push this ball so that it get, let's say, a pushing force which provide the acceleration at any position. So this acceleration is provided by the pushing force from the outer wall of the tube. But here, once the ball leaves the tube, there's no any pushing force from the tube. Then which direction do you think it will go? Due to the Newton's first law, it will keep going in the direction of C, because at this moment, the instantaneous velocity is going in the direction of C. If there's no any other forces, it will keep going in the direction of C with a constant speed. So the answer is C. Okay. Now let's see one example to calculate some force or acceleration. What's the maximum speed with which a 1,500 kilogram car can make a turn around a curve of radius of 20 meters on a level, or means unbanked road without sliding? This radius turn is about what you might expect in a major intersection in a city. So it's a very common question in a very common corner. Okay, now let's see. We want to calculate what's the maximum speed. So what's the speed, which is v. We want to calculate v, and we have a mass of the car and a radius of the turn or the circular motion. And if you search the table, coefficient table, you will find the coefficient, the static friction coefficient is 1.0 between tire and the surface of the road. So we know all of this. We want to calculate the V, and we know A equals to V squared over R. So MA equals to M times A equals to F, which is net force. So this is Newton's second law. Net force equals to MA, and MA equals to MV squared over R. And here, net force is actually, as we said, it's your friction. That's the static friction between tire and the surface of the road, which is mu m. Do you remember this equation? Fs equals, or the friction equals mu times n. N equals to weight, because your car is on the surface of the road, so N and weight, they balance each other, and weight equals to mg. This is the way we calculate the weight. Weight equals to mass times g. So here you will have mv squared over r equals to mu mg. So let's see if you know mu mg, and if you know m r, the only thing you don't know in this equation is v, so you can calculate the v. Okay, so this is a similar thing discussed here. So mv squared over r equals to mu mg. So v equals to the square root of mu g times r, and then you have the final answer, 14 meters per second. Okay, 14 meters per second is about 30 miles per hour. So in the true case, in the real case, when you drive the car at the intersection, when you make a turn, please make sure you don't want to drive too fast. It should be less than this speed. If you are too fast, then maybe your tire cannot provide the enough frictions, then this turn will not be made successfully. So there might be some accident happen. So make sure you drive slow at the corner. Okay, so this question, this problem shows how fast can you drive on the unbanked or level road surface at the corner. But sometimes on the highway or on the racetrack, sometimes there's a banked road, as shown here. A curve on a racetrack of radius 70 meters is banked at 15 degrees angle. At what speed can a car take this curve without assistance from friction? So first of all, let's see why the road has to be designed in a banked way. So this is theta. It has a theta or angle between horizontal and the surface of the road. Because let's take a free body diagram here. In this case, the normal force on the car is perpendicular to the surface, which is in this direction, and the weight is in that direction. So the normal force can be divided into two components, x components and y components. Y components of the normal force will be, let's say, balanced by the weight, but the x direction of the normal force, it could be used for providing the centripetal force, which gives you the centripetal acceleration. And um, can you calculate the x component and the y component of the normal force? The answer is yes, if you know the weight of the car, because the weight of the car equals to the y components of the normal force. And then if you know the theta, by using some trigonometries, you can calculate the x components. Okay, now the question is, at what speed can a car take this curve without friction? Or if there's only the normal force and there's no friction, so what speed should the car uh, should the car be um, be running um, during this turn on the curved on the banked curve? Okay, so still um, we know the radius is 70, so v equals to uh, a equals to v squared over r. This is the centripetal acceleration, and the centripetal force F equals to ma or m times v squared over r. That's the centripetal force, and the centripetal force actually is provided by the nx, the x component of the normal force. And the x component of normal force provided the mv squared over r. Now let's talk about the ny. So y component of the normal force equals to weight or mg. Okay, this is another equation. So in this equation, it describes the nx, and here it's ny. And you know, nx over ny, it's tangent 15 degrees in trigonometry, because this angle is 15 degrees. So nx over ny, that's tangent 15 degrees. And then if you know this value over that value is 15 tangent degrees, you can calculate the v, because you know r, you know m, you know g, and you know the ratio between mv squared over r and mg is tangent 15, so you can calculate it, which is shown here. So finally you can calculate v equals to square root of rg tangent 15 degree, which is 14 meters per second. Okay, maximum walking of speed. So you can read this and try to understand how to do the calculation. We don't want to discuss too much about similar calculations. So here, in next section, apparent force in circular motion. If you're a passenger in a car that turns a corner quickly, it's the force of the car's door pushing inward towards the center of the curve, which causes you to turn the corner. So what you feel is your body trying to move ahead in a straight line as outside the force act to turn you in a circle. So your body wants to go this way, however the car will push you so that you can change your direction of the velocity from this direction to another direction. This is a centrifugal force. Centrifugal force. So this is centripetal force will never appear on the free body diagram and never be included in Newton's laws. So this is the force that you feel. Okay, now let's see the apparent weight in circular motion. Let's say in a roller coaster, you may have a motion like that. So at the bottom of the roller coaster, the velocity is going this way, and the acceleration is going up towards the center. So if the acceleration is going up, then your net force should go up. Then in free body diagram, if you show normal force and the weight, the normal force should be greater than weight, so that the net force is going up. In another case, at the top of the roller coaster, the net force should go down because the acceleration is going down. So the normal force and the weight should be like that. So the force you feel, which is your parent weight, remember that the parent weight is the normal force you feel. So the force you feel is the magnitude of the contact force that supports you. In this case, it's normal force. In this case, it's normal force too. When the passenger on the roller coaster is at the bottom of the loop, the net force should be greater, so you will feel heavier. Her parent weight is greater than the weight, so it feels heavier. And Newton's second law for the passenger at the bottom of the circle is the net force equals to weight plus the normal force, and the weight is going down, so it's a negative value, which is equals to the mv squared. From this equation, the passenger's apparent weight is normal force, and the normal force equals to W plus mv squared over r. And her apparent weight is greater than her true weight. That's why when you are in a roller coaster, if you're at the bottom in a loop, you will feel heavier. In another situation, when the passenger is at top, then the net force equals to normal force plus weight. So here they use x. Actually, they're not in x direction, it's in y direction. So the normal force plus weight, and this time they're in the same direction. It equals to mv squared. So finally, normal force equals to mv squared over r subtracted by the weight. If v is sufficiently large, her parent weight could exceed the true weight. And as the car goes slower, there comes a point where n becomes 0. If n is 0, then that means mv squared over r equals to weight. Then this speed at which normal force is 0 is called critical speed. Critical speed happens when this value is 0, or when mv squared over r equals to weight. Then vc, or critical speed, equals to the square root of rw over m, or w, or the square root of rmg over m. M and m is cancelled, it's square root of gr. So the critical speed is the slowest speed at which the car can complete the circle. Okay, now let's see several questions. A textbook swings back and forth as a pendulum. Which is the correct free body diagram when the book is at the bottom? Okay, so which one do you think is correct? So the answer is C, because you have, in this circular motion, you have a centripetal acceleration going up, so the net force should go up. And here, If the car is going in this way, what's the free body diagram? So the answer is A, because in this situation, in this circular motion, the centripetal acceleration is going down, so the net force should go down. Only A is the correct answer. A roller coaster is going in this direction. So which free body diagram shows the force on the car at the top of the loop? Rolling friction is neglected. Okay, so which one do you think is correct? The answer should be this. Because, first of all, the normal force should go down and it should have a weight. So the weight and the normal force provide the centripetal acceleration, and that's the direction of your net force. Centrifuges. So when you try to swing your arm in a circle like that, you will feel some blood pressure at the tip of your finger or tips of other fingers. This is because um, in this way you're trying to generate centrifuge using your arm. The high centripetal acceleration requires a large normal force, which leads to a large apparent weight. So in this way, your apparent weight of your blood is heavier than normal. So they all um, generate some pressure to the tip of the fingers. Okay, now let's see one example here. One 18-centimeter diameter ultracentrifuge produces an extraordinarily large centripetal acceleration of 250,000 gram, where g. Sorry, it's 250,000 g, where g is free fall acceleration. And what's the frequency in the RPM? And what's the apparent weight of a sample with a mass of 0.003 kg? Okay, so first, let's convert this acceleration into SI unit. So we know g is free fall acceleration, which is 9.8 meters per second squared. So A is 250,000 times g, which is such a big number. And then we're asked to calculate the frequency in RPM. We have learned A equals to, do you remember the equation of calculating acceleration here? Let's go back to the equation of the acceleration. So A equals to 2 pi f squared times radius. So f and A, they have a relationship like that. Using this equation, if you know acceleration, you know radius, you can calculate f. F equals to square root of it equals to 1 over 2 pi square root of A over R. If you take all the numbers in, you will get the answer. It's 830 revolutions per second. However, we're asking revolutions per minute. Then let's calculate from revolutions per second to minutes. So 1 second equals to 60 minutes. So you have 50,000 revolutions per minute. That's a very fast rotation. Okay, second, what's the apparent weight of a sample with a mass of 0.3 0.003 kilogram. Okay, we're trying to calculate the apparent weight. So apparent weight equals to net force. It's ma. So you know m, you know the acceleration, so you can calculate um, the number of the apparent force, which is about 1,700 pounds. So a 3-gram sample weighs about 1,700 pounds. So that's a huge force in the ultracentrifuge. Okay, now let's see some more examples. A coin sits on a turntable. As the table steadily rotates counterclockwise in this way, what force or forces act on in the plane of the turntable? So, which one do you think is correct? The answer is A. So there's only one force, which is friction, providing the centripetal acceleration. There's no any other forces. And still a car on the turntable. Uh, the free body diagram below shows a car from behind moving away from you, which is the correct free body diagram. Okay, so the answer is C. Why? Because so first of all, the acceleration pointing to the center, and the normal force and the weight, they balance each other. So the answer should be C. So seems like uh, the A is wrong, maybe because I don't know why A is wrong. Maybe because it's labeled R here. Maybe R means the center. I don't know. But from this um, figure, we can say the normal force and the weight, they balance each other, and the friction provides the centripetal acceleration, which pointing to the left. So C is correct. I think A is correct too, because A and C seems like they're the same. So the only thing is R. So I don't know why the center of the circle is labeled as R. Usually we don't label the center as R. If the center is labeled as R, then C is only answer. If not, then A is correct too. Okay, a car turns a corner on a banked road. Which of the free body diagram could be the car's free body diagram? So first of all, let's see how many forces are on the car. Number one force, weight. This is a must-be force. And then normal force. And then there might be friction and there might not be frictions. If there are some frictions, it might be going up or down because we don't know if the car is sliding up or down. If the car is too fast, it will try to slide up. If it's too slow, it will try to slide down. So it depends on if the car is fast or slow. So the friction could be going along the ramp up or down. So the correct answer could be E. Okay. Circular orbits and weightlessness. So finally, we're talking about the orbits. Now, let's see orbital motion. The force of gravity on the projectile is directed towards the center of the force. For example, um, let's say if you try to throw something from the surface of the Earth, if you throw let's say a ball. If you throw it, the ball, if you throw it horizontally, the ball will go in a projectile motion. It will go to the right and down. It will fall here. If you throw it hard, or if you throw it in a higher initial velocity, it will go further and down. If you throw it even harder, then it will go in this way. If you throw it even harder or even higher velocity, it will go here. So if you throw it very, very fast, then it might go a long way here. If you throw it more hard, then it got higher initial velocity. It might go way here, and finally it falls here. And then it keeps going in a circle. So it will go circle by circle by circle. So the projectile motion becomes an orbital motion. So this is the uh, mechanism of launching a satellite. So the satellite is always in a free fall. It's like you're throwing the satellite uh, in a very high initial velocity, so that when the satellite is falling, it it makes a very long trajectory, and finally it becomes an enclosed trajectory, and then it keeps going in an orbital motion. So it becomes orbital or circular motion. So there's nothing special for um, let's say launching a satellite. The mechanism behind that is very simple. Due to the gravity force, if you throw it in a very high speed, it will automatically uh, in a orbital motion. If the launch speed of a projectile is sufficiently large, there comes a point at which the curve of the trajectory and the curve of the Earth are parallel. Such a closed trajectory is orbit, and orbiting projectile is in free fall. The force of gravity is the force that causes the centripetal acceleration of orbiting objects. And here A is mg over m, because um, A equals to net force over m. This is the Newton's second law, and the net force is weight in this situation. Weight is mg. So finally, A equals to g. And an object moving in a circle of radius r at speed of v orbit will have the centripetal acceleration if A equals to v squared over r, which is g. That is, if an object moves parallel to the surface with a speed v equals to square root of gr, then it will be in the orbital motion. So the orbital speed of the projectile just skimming the surface of smooth airless Earth is, let's using this equation and use the g at the surface of the Earth and the radius at the surface of the and the radius of the Earth, then you calculate it's 7,900 meters per second. We can use v orbit to calculate the period of satellite, which is t equals to 2 pi r over v, and then that's the equation to do the calculation of the period. So in orbit, the satellite or the object is in a free fall motion. So the astronauts and their spacecraft are in free fall. Now, some quick questions. Astronauts in the International Space Station are weightless because what? I'll give you some time to make your choice. Please pause the video. Okay, Now, I guess you have to make your choice. So they're all in free fall. Okay, the moon, like all satellites, is simply falling around the Earth. If we use a distance to the moon um, to calculate t, which is 2 pi over v, you will have the period is about 11 hours instead of 1 month. So this is wrong. This is the wrong calculation. Because in this case, we shouldn't use g to be 9.8 meters per second squared. Because the g equals 9.8 only when the object is at the surface of the Earth. But the moon is not at the surface. It's far away from the surface of the Earth. So the g becomes a different value. Now let's see how to calculate the g or acceleration between moon and the Earth, actually between any two objects. So first, let's introduce Newton's laws of gravity. Gravity is a universal force that affects all objects in the entire universe. Any two objects has interactions. Such kind of interactions is the gravity. Newton proposed that the force of gravity has following properties based on experiments or observations of stars and other planets. So the properties are: first, the force is inversely proportional to the square of distance between the two objects. Means when the two objects are farther away, the force becomes smaller. Second, the force is directly proportional to the product of the masses of the two objects. And by including the two properties, he developed the equation of gravity um, equations, which is F equals to G m1 m2 over r. G is a gravity constant. m1 m2 are the mass of the two objects. R is the distance between the two objects. And the value of G is constant, and we will learn it later. Let's see one example here. A gravitational force between two lead giant lead spheres is 0.01 Newton when the centers of the spheres are 20 meters apart. What's the distance between their centers when the gravitational force between them is 0.16 newtons? Okay, from 0.1 Newton to 0.01 Newton to 0.16 Newton, it's 16 times bigger. When the force is bigger, when the gravity is bigger, we know they are closer due to the Newton's gravity equation. It's 16 times greater. That means they're 4 times closer, or the distance is 1/4, because the relationship between force, the gravity force, and the distance is inverse squared. So the distance should be 20 over 4, which is 5 meters. Okay, another calculation. You're seated in your physics class next to another student 0.6 meters away. So estimate the magnitude of the gravitational force between you. And the mass of you are 60 kilograms. Okay, you know the mass, you know the distance. Then you can calculate the gravitational force using this equation. G m1 m2 r squared. m1 is 65. m2 is also 65. r is 0.6. So you can calculate it. G m1 m2 And here it gives you the gravitational constant. It's a very small value. It's given. It's given or observed or measured by some experiments, and that's M1. That's M2. After the two mass, you will have F here. So the force is pretty small. So usually you don't feel there's a gravity force, there's a gravity between you and another person because it's too small. Okay. If you travel to another planet, your mass will be the same. However, your weight would vary. The weight of the mass m on the moon is given by weight equals to mg moon. Using Newton's law of gravity, the weight is given by F moon on m equals to g m of moon, m of the object over the distance between the object and the center of the moon, which is the radius of the moon. Since these are two expressions from the same force, they are equal, and g planet equals to g uh, which is gravitational constant times the mass of the planet over the radius of the planet. So that's the equation of calculating acceleration on the surface of a planet. You just need to know the m of planet and r of planet. M is the mass, r is the radius. Okay, if we use the values for mass and the radius of the moon, we can calculate the gravitational constant on the moon is 1.6. So a 70-kilogram astronaut wearing 80-kilogram spacesuit will weigh more than 330 pounds on the Earth. However, it's only 54 pounds on the moon. Okay. Now, let's see one example here. Mars has two moons, each much smaller than the Earth's moon. The smaller of those two bodies, Deimos, isn't quite spherical, but we can model it as a sphere of a radius of 6.3 kilometers. Its mass is 1.8 times 10 to 15 kilogram, at which speed would the projectile move in a very low orbit around Deimos. Okay, the calculation is pretty straightforward. We have learned the way to calculate the gravitational constant or small g on any planet. It equals to the gravitational constant, which is capital G, times the mass of this planet over the radius of the planet squared. So if you take all the numbers in, the G is 0.003 meters per second squared. Remember, on Earth it's 9.8. So on Deimos, it's a very small gravitational constant. And then we can use the equation to calculate the speed of the orbit on the surface of the planet, which is square root of gr, and then you get 10 miles per hour or 4.3 meters per second. It's very small velocity or very slow. With a good jump, you could easily launch yourself into an orbit around Deimos. Okay, gravity and orbits. So Newton's second law tells us the gravity equals to ma in a free-fall motion or in an orbit. So the F is the gravitational force of the larger body on the satellite, and A is the satellite's acceleration in this situation. And because it's moving in a circular orbit, Newton's second law gives um, G over r. This is Newton's gravitational equation. It equals to ma or mv squared over r. By combining this equation, you'll finally have v equals to square root of gm over r if you combine this equation. So a satellite must have this specific speed in order to maintain the circular orbit of radius r above the larger mass m. So for a planet orbiting the sun, the period t is the time to complete one full orbit. The relationship among speed, radius, and period is the same for any circular motion. So v equals to 2 pi r over t. Combining this equation of v for circular orbit from the previous equation, you can get this equation. And finally, if we square both sides and rearrange the equation, you will find t squared equals to this equation. Okay, so there are some quick questions. You can read it and think about the answer. Communication satellite appears to hover over one point on the Earth's equator. A satellite that appears to remain stationary as the Earth rotates is said to be in a geostationary orbit. What's the radius of the orbit of such a satellite? Okay, even it doesn't mention that, but we should know if it's a geostationary orbit, it's spinning or rotating with the Earth, then the orbit of the satellite will have a period to be 24 hours. Even if we don't say it in the question, you should know that. In seconds, 24 hour means 8.64 times 10 to the power 4 seconds. And you can use the previous equation to calculate the radius, because you know t, you know mass of the Earth, you know g, you know pi, they're all constant. Then you can calculate the radius. So finally, it's 4.22, 10 to 7 meters. Okay, so the gravity on the grand scale, no matter how far apart two objects may be, there is always a gravitational attraction between them. And galaxies are held together by the gravity forces. All of the stars in the galaxy are different distances from galaxy's center, and so orbit with different periods. Okay, so that's all for this chapter. This chapter is mainly about circular motion. It has a lot of equations. If you can't remember all the equations, you can just maybe write it down on a cheat sheet. And when we have the final exam or when you're doing the homework, those equations can help you. So talking about the final exam, the final exam will keep the same. It will be 20 multiple questions. I will give you about 18 minutes to finish all the questions. You will do it at home. I'll give you the question sheet and you will finish it in 80 seconds and send it back to me via the Google Drive. You will upload it to my Google Drive and then I'll grade it for you. Okay, so that's everything for chapter 6. So I'll see you in chapter 7. Bye bye.